this thrust load on this direction, if you go the other way, basically you are dismantle the part, your inner ring will be, you are trying to disassemble the inner ring from the outer ring. That means the best way you have to refer that one. Okay, that's a specific one, misalignment. 2 row, okay, this is a thrust load as well. Right. Then it will be the what I call it, the bearing. You take into consideration when you select bearing. Okay, for example, let's say the basic bearing life equation will be the same regardless of the type, regardless of the type of Timken or whatever SKF or juvenile will going to be the same. Is actually the life, the force time life on over A equal to constant, based on that equation, because when we refer to the catalog, and this is depend on catalog, different catalog maybe have different load maybe have a different life. For example, in our case, our life going to be, okay, let me have here, let me show you bigger here. Our life going to be 90 million revolution, and with 90% percentile, what it means that, for example, if I give the load here, equivalent load, and it doesn't matter, it's going to be a combination of the thrust and the radial load. That's an equation that govern that the relationships. Okay, if you put 100 of this 10 millimeter L00 type bearing, 100, 10 will fail. That means 10 will show the characteristic of failures. The only 90 will survive. That means there's 90% percentile. Okay, this is going to be the what I call it, the serrated is going. We have to refer this one because when we choose this, when we use this value here, right? That means we're going to choose this one, based on that value. Because of that, this is going to be the this is going to be the one that we are look for. This is going to be your design. This is going to be your the main idea here. Regardless of the type, this is going to be your design, because design might have a different design spec, whatever design. Let's say design criteria. Let's say I just mentioned criteria here. All right. Maybe the different loads, different life. Instead of 90, maybe you want to have 1,000 million, whatever, one different type of life and different abilities and so on. Okay, because this is equal to constant, because we are also refer to the C right here, therefore we got this equation. This is going to be basic equation. Okay, if you refer to the books here, you be careful. The basic equation will be based on this equation. Going to be 14.1. Okay, because of it's a bit different for juvenile. I just mentioned this one for juvenile. It assume A going to be 10/3, regardless of whether the A is for ball or cylindrical. 10/3. That is juvenile. Assume that value. All right. This is for juvenile. A equal to 10/3. Maybe it will design safer. The value going to be larger when for equal to 3. That's the main reason there. Okay. However, certain catalog maybe specifically designed if A for ball bearing going to be 3, A 10/3 for roller and tapered. Be careful. You have to check this value. For juvenile, we have going to be 1/10/3. All right. There's two equation here. Okay, this equation is the basic equation. Okay, except for the A value. All right, is applicable for all type of bearing. This is going to be the basic equation. Right? Maybe certain other books, you not assume A equal 10/3. You're going to assume A going to be 3 or A 10/3. Certain catalog. Okay, this is going to be the basic equation. However, take note, 14.5. That you have to use the formula here, because the 14.5 will take into consideration of the application load factor, which is basically a safety factor to the load. Okay, and as well as the KR with the factor, reliability factor. If, for example, let's say you design for 90% reliability, the value cannot, the different life factor here. That is the two things. Okay. Okay, this is going to be the life. The life of the design will be in revolutions. Okay, you can use this equation, 60 RPM time what the revolution, this rotation speeds and design in hours, That will be the life of the. Then you get this value, Okay, what make the difference between catalog is this value, FE. All right. The FE for example, let's say for radial load only, radial load only, that means your FE will equal to FR. That for sure, that F equal to FR. No need to have it. However, when they combine, combine of radial and thrust, right? That means you have to refer to the FE is bad, you must refer to catalog, Right. In the case of our, we have three type of bearing. Okay. We have three type of bearing here for the roller. Okay, because roller only take radial, we can go straight to this formula. All right, F equal to FR. Even for the other two, for example, let's say if the radial ball and angular ball take only radial load, for example, there's only radial load, we can use the basic equation here, right? Okay. Okay. However, when there's a thrust load and radial load, we have to refer to the specific catalog. We have to specific equation of catalog. In our case, we have to refer to our equation in the book. Or SKF, you to refer the SKF catalog and so on. The main idea of the FE equivalent here is how much the ratio of X of the radial and thrust take into account to form the FE. That's the basic thing. Okay, basically, for radial ball bearing here, this is a very specific catalog. If the FT over R is less than 0.35, basically the thrust has no effect. But that's what it means. Only that equal to radial. In between that to 10, the ratio between FT and R, this will be the equation. And finally, if FT larger than 10, we only take value of 1.176 of thrust load. And this is how much the relationship of the radial and thrust load to be taken into account. And this is going to be very specific equation for specific type of bearing, even within a single catalog. SKF, okay, you have radial ball, different formulas, angular ball, different formulas. You have to refer to that. SKF. In this case, we have radial ball and angular ball. This radial ball, angular ball bearing. If the ratio different, for example, for the FTFR, going to be 0.68, F equal to FR. In our case, the example before that, we got our ratio going to be FT over FR. In our example, going to be equal to 0.494. We're going to use the second equation for the radial that we done last time. Is it right? And we use the first equation for the radial. This we haven't done yet. Okay, right. Okay, that will be the idea. If maybe 0.5, maybe 5, going to be different formulas and so on. You have to refer to this equation basically. All right. Okay, this is the example that we have. Okay, we have done the free body diagram. Okay, we have done the, based on this one, this is going to be a radial load. Okay, this can have a axial load here and radial load. That means the possible answer here is going to be have a angular radial ball, or this is a radial ball or an angular ball. That's the possible solution here because there's a thrust load here. For B, all type can be used. We can have roller, we can have radial, we can have angular. Meaning that there's a possibility of 6 solution here because three solution. Remember the 3 solution here. For each one, there's a 3 type of classes here: 0, 0, 200, 300. That means there's 3 possible solutions from radial ball. Another 3 possible solutions for angular ball. There's 6. When we have for radial only, we have another 3 for roller. That means 9. That's the main reason we have to have this one going to be 9 solution. In the case of the test, you can just list down all the, for example, let's say the possible bearing. However, in the project, you have to integrate the solution with bearing and with shaft. Because, for example, let's say you have a number of solutions, and then the shaft, there's a certain diameter of shaft, then you can select the right bearing. Okay, that's the main reason. Okay, now we refer to our example. All right. This that we have done before that, this yesterday. This is going, okay. Okay, this I think this the adjustment we have initially done that I mentioned before this. Since the thrust or axial load at zero bearing O must withstand thrust, and therefore the radial angular can be used. And this actually positive solution. No thrust no thrust at all at B. All the type of bearing can be used. This is possible solution. Okay, this the basic free body diagram. Right, then we found out that this will be the load. For example, at O there will be a radial load 600 or 6.8, SL will be 300, and the bearing will be radial 1000. Bearing B, radial only 1645.4. Okay, the ratio will be this ratio. I think we are okay. The ratio is going to be 494. That's what I mean here. When we have 494, we're going to use different formulas. For in the case of yesterday, what we did yesterday, we is it Sunday? Okay. First of all, we calculate the bearing calculation. This is going to be the same. This is going to be the design life, the equation, life, and so on. This will be regardless of all the shaft. The bearing on all these shaft going to be the same. Let's say we take this shaft. This is going to be the same bearing parameters and sell this one because the shaft rotate at the same speed, and for example, the same number of revolution and so on. Okay, that will be the same. Basically, when we insert this equation, when we have the equation, we find out this is for the radial bearing. We found out that it's 4.94. We use the second equation here. That means this will be F equivalent here. Then we convert because remember this was in kilonewton, right? I think this was, then we convert to kilonewton, we got 3.13. Okay, this is what I mentioned here. This is going to be the same regardless of bearing type of bearing. All right, this value going to be the same. This ball radius going to be the same, except for the difference only the equation here. Right. Okay, that means which equation you use to find the equivalent. Okay, in this case, we are use radian only. We can got F equivalent going to be, you insert all the value, got 8.91. Okay, then we have to choose larger than 8.91. The LC0 going to be 65. 8.91, 9.4, the possible 40 diameter. Okay, and finally 8.91, we can choose the larger, a bit larger one, 35 for diameter. This will be the solution. L0 SLT bore diameter going 65. 200 LT bore meter is going to be 40 millimeter. 300 medium here going to be 35. These are the three possible solutions from if you choose radial ball bearing. Okay, I think that we defined yesterday. Now, for today, we're going to proceed with the second one. All right. I think it's going to, the procedure is going to be the same. The procedure is going to be the same. You find the ratio here, already find the ratio, choose the equation, F equivalent, and choose. All right, a bit similar. You can refer to your note yesterday. All right. Okay, can you find the solution number 2 now? Let's say I give you 8:25, 8:30. We can discuss solution number 2. 8:30. Right. You have question, you write on the chat. I will try to answer that. All right. 8:30, we can discuss the solution angular ball bearing. Yeah, she's on the chat. You have question, you can write on the chat. Right. 8:30. Okay, Assalamualaikum. Okay, right. Angular contact, we have the FT is for the ratio going to be 0.494. Ratio is 0.494. We should use the first equation now. This is going to be the equation we use. That means only the radial load, equal FT 0.94, FE equal to FR, FT, FR equal to 606.8, that means equal to 2.7, convert back to kilonewton. Then we insert this equation to the basic equation here. Okay, I mentioned this one, this is going to be the same, if you already calculate that, you don't need to have calculate every single time, just put the value here. This value can be used for all the bearing on that shaft. It's going to be the same. Let's say certain value, you just type that value. You no need to press the calculator every single time. Okay, 2.7, 1.2, okay, 7.68 kilonewton. Alright, based on that, we have the angular ball. We have angular ball. The next one will be 9, 55 millimeter ball. 7, 6, 8.2, 35, and 8.8. Okay, 6.76, right? This is okay. That means this will be 30 millimeter. That is the solution here. We have 3 solutions for the radial ball, and we have 3 solutions for angular ball. Roughly, when the thrust load, there will be 6 possible solutions. Not to worry, you just list down the solution. Every single solution, which one to choose? It depends on the interaction of the shaft. Maybe the question after that will test you whether which one to choose. All right. Any question? I just stop you here. Any question for now? Or we can continue. All right. Any question? All right. I think is straightforward, the method, except for, I think why the difficult part is the free body diagram. Again, meaning that if you make a wrong mistake in free body diagram, your selection is wrong. All right. That is the not nice thing on the bearing, even for the test. If you make mistake on variable diagram, you make mistake on your F equivalent, that means your selection is wrong. All right, be careful on it's very important, the free body diagram. All right, any more question or I can proceed? Okay, I proceed, All right. Okay, now we have done that. Okay, we should proceed to the radial, bearing B, right now the bearing B here. Okay, for the bearing B, because it's only radial, we could go straight to equation 14.5, with F equivalent to FR. That means the C rated or C required here can be used for all 3 type of bearing. Not to worry. That means because only the F equivalent, the equivalent here going to be FR. That means this value can be used for 3 type of bearing. All right, can proceed with that. Okay, I think going to be the FE. All right, FE going to be okay. This the value 7.3. All right, then can you do this until I think quite 8:57, 37? I think quite fast, because you are familiar with this one. 8:37. Another 4 minutes. Okay, right. Okay. Straightforward, still required, or still rated. Okay, 20.83. Okay, we have all this solution, 20.83, make it smaller now. Okay, 20.83, the first one will be 21. Radial going to be 105. Diameter 200 going to be ball, going to be 22.5, 85 diameter. 21, 20.3, which is 22.65. That will be solution for the radial. For angular, going to be series, the first series going to be 95. The second series going to be 200 series, going to be 22.5, going to be 18 meter diameter bore. And finally, the 300 series medium going to be 55 millimeter. This is the roller, 20.9, okay, 100 millimeter bore. 1,002, this 1,000, it's not 100, and then 1,002 going to be 65, and finally 1,003 going to be 45. This is the possible solution, 9 possible solution. Okay, let's take one example here. We'll take one. We proceed with this one just for the sake of understanding what is all about how to select this one. Okay, if the rotating shaft need to be 1.5 inch, let's say 1.5 inch. Point O is fine. Point O is fine because point O, you should check the if you go point O, okay, let's say we go the example here. If you go for the bending stress, the bending stress is going to be very small. This is going to be the bending stress for point O maximum. Let me draw a line here. This point O roughly going to be here. The bending stress is going to be a bit small. But point B is quite critical because point B, the position of point B is the middle of the diameter. It's very difficult. Okay, let's say based on that calculation, we point B will be a bit critical. Point O, because let's say we have a shaft diagram here. Let's say we have just like this. Let's say my moment diagram, the value is going to be small. But you have to double check whether that the diameter of the shaft is is okay or not. Okay, however, this is going to be very, very critical. Right. Okay, let's say 1.5. Instead of 1.5, you go have to this solution here. 1.5. Okay, let's say 1.5 times 25.4. Okay, I want to check in what is in millimeter. I'm going to be 1.5 times 25.4 equal to 38.8 million. Okay, one shaft is going to be 1.5 inch. Okay, 1.5 inch equal to roughly 38.1 millimeter. Okay, what is the possible solution here? All right. Right. The best solution will be 45 millimeter. But you're right. You cannot choose lower than that. All right. All right. 105 is too large. 85, 95, 45. This will be solution. Meaning that what you do, you have to increase the shaft by 45 millimeter. That's the solution now. That means the shaft is safe, the bearing is safe. Okay? Don't, for example, reduce the bearing to, let's say, to 40. That means the bearing will fail, but the shaft is okay. That means you have to make sure both is fine. In this case, that in order to both is fine, you will choose 300 medium bore 45 millimeter, and you have to increase the shaft by 45 millimeter because the minimum diameter shaft 38.1. That means go increase by 45. That will be a lot safer. All right. Based on that, then rely on the shaft dimension. That will be the decision. At the end of the day, if you refer to the books here, on the first table here, is the geometrical. If you choose that one, you have the certain value here. You can find what is the radius, what is the width, and so on. Okay, this will be, for example, the radius will be this will be the diameter of the ds is what is the diameter of the shaft. The ds is going to be diameter of the larger shaft. That means it's going to be value here. Okay, the RE going to be, I think, going to be the radius of the fillet of the shaft. All right. That means then you refer, if you choose that bearing, refer to this value. to get, for example, let's say you have a bearing here, you have a larger diameter. What is the larger diameter? Do you know that is 45? Let's say we check the 45, we use the roller, the 45, the roller 45, 45 roller here. I think which one we are choosing? Let me check the example here. We are choosing the 300 series, the 1300 series, 45 roller 45. This one, that mean the diameter of the shaft here is going to be 55.9, and the radial fillet is going to be 2.0. That means the shaft diameter here is going to be 55.9. This is going to be your radial fillet going to be, what the value? Is 2.03, is not mistaken, double check, 2.03. And the width and so on. That means this will be your final dimension of the shaft. Okay, that will be in for the purpose of the project. Yes, you have to, after you get the gear, then you calculate the bearing. After that, you can go for shaft. The shaft, go to parallel double check the intention of shaft. Whether after this, for example, like in this case, in this example here, you found 1.5, you got 45, then the shaft, and after that you can, or you can use the suggested diameter by the for example the DS here. All right, then with all the inner bore diameter with the radius, check whether the shaft is filled or not. That's the other way around. And that means the shaft will be finalized. That is fine. That will be for the project. Okay, I give you 2 minutes to go through all the example above. 2 minutes. If you have question, you can proceed. 2 minutes, 8:45. You can discuss after that. Any question you can ask. Go through the example. All right. Any question regarding the example? It's a good question. You can the iteration on bearing as well at the end. Which one to choose that is applicable for your, for example, in your project? Any question? All right. I can continue then. All right, and these are some concluding remark on the bearing. Matters to consider when selecting a bearing. Okay, from the example, okay, I mentioned before that, what you have to do is just you look at the equation, and insert the equation, you plug all the numbers, you got the solution. Okay. However, in the real world, in the real design process, there is a wide range of bearing selection. There's so many types of bearing selection. Okay, in the case of, I take the example from this is SKF, a number of bearing type, SKF deep groove ball bearings, single double groove, angular contact bearing, 6 type, and so on. There's so many type of bearing. In our case, we have 3 types. Okay, they have so many type of bearing. Apart from that, for each type, there are 4 series number. That means there are various solutions you can choose. One thing that is very important, there's so many types and so various. That means the solution we have here, maybe the solution at the end of the day, you can select the bearing. Not to worry, because our catalog is very limited. Okay, if you go for SCAF, you can find a better catalog and better wide range of solution. And that is one thing. Right. That is what you have to consider, the thing that's considered bearing. Parameters that are important, I think we discussed this one. Okay. The bore diameter or inner diameter will be must fit the shaft. Okay, outer diameter must fit the dimension constraint or the what I call it, the, because certain bearing, if you go, you for the sake of your own knowledge, you can download the SKF. They sell as well the bearing housing. That means to where you can mount the bearing, the outer diameter. Okay. This is quite important that we not cover in the, for example, in our course. Deflection of the shaft must be very, very minimal. For example, for misalignment bearing, the bearing, what is misalignment bearing? The bearing that the ball is moved, the ball bearing here move here. That means when the inner deflect, the ball will move. For that thing, that design for misalignment is only allow you to have 1.5 to 3, is not mistaken. 1.5 to 3 degree, 1.5 to 3 degree. That means very small. Imagine, if you don't do misalignment, that means only allow you only 1.5 degree. That means the deflection is very, very small. However, in our case, we never take consider of the deflection. Okay, you must take consider of the deflection then. Okay, this is the very selection of the shaft. There is the inner shaft here that will be inferred, and this will be DS proposed by the housing and the radial shaft and so on. This will be relationship with the shaft and bearing the shaft. All right, bearing loads and if possible selection. I did mention this one as well. For example, let's say in this case, the direction of load. These are taken for SKF. I take this the figure for SKF. You must consider where is the load, the thrust load. For example, this 3 type of bearing selection here, all right, is only allow you, this is only allow you thrust load from the top. You cannot have a thrust on the bottom, or vertical, or doesn't matter. Vertical can be on the left or right. Make sure in the right direction. For this double row thrust load, can have on top and bottom, and this one, okay, have top and bottom with a small with a radial load as well. Right, this is very important. I think I did mention earlier. The certain bearing are very specific. If you don't follow this one, basically the load is the load is actually how the bearing transfer the load to the housing or to the bodies of the device. At the end of the day, transfer to the ground, okay, or to whatever. Is how if you putting the load on different way, you are basically you are dismantling or you are disassemble the bearing. You assemble the inner and the outer. It's very big. You have to take care of that thing. Okay, bearing conventional life. This is going to be the bearing conventional life is useful for the project. You have to assume certain hoist, hoist. You have to assume what is the service and so on, what the load, and this is going to be the bearing conventional life. Table 14.4 in your books. In the 1,000 hours, not in the hours, 1,000 of hours. I mean 1,100 hours, and so on. Okay, that will be the thing consideration. I think we discussed the thing. It is keep repeating. All right, this is the project. Okay, in your case, some because of the design only maybe you have 2 pair of bearing. It's 2 pair of bearing. Gear, and then you have 2 gear, because I see I go through some of the design. There is motor here. All right, this is the first pair. All right, the second pair and the third pair will be here. All right. For gear, all right, for manual calculation, okay, one person will do this one, second person will do this one, this one person here, second person will do here. For the group is 3 person, maybe you can use different module here to test. Let's say your friend use module 2, or you can choose number 1, you can use a different module. Right? But the same calculation, that means you have 3. But in this case, you will have 3 shaft. Is it right? For sure, 3 shaft. The first shaft from motor to the first pair, and second pair, and third pair. That means you have 3 shaft. Choose 1 shaft for each of you. That means for each shaft, at least must have 2 bearing. Is it right? For example, in this bearing, this is bearing. In this one, maybe you choose bearing on this one, and so on. This is overhanging. They're very careful here. Okay, and this with the hoist case, then maybe you have bearing here. Then you have to have the bearing. And we mean that 1% will follow for stretch of 2 bearings, both bearing, like this in question, and the shaft. All right? Okay? Select bearing based on shaft base. However, if you go through this one, you find out that only the load will be, there's no thrust load because we are using the no axle load or thrust because using the spur gear. The spur gear, there's no axle load, right? Because of that, okay, assume thrust load on the shaft. You have to assume that 7 times of the radial load. Let's say you have both here, okay, or choose the smaller radial load. For example, you have both radial load here, choose the smaller one, the radial load will be 7 times of that load. All right, select the suitable bearing. That means you have 1, 2, 3, right? This one, okay, 7 times, let's say find out this one smaller one, times 7, and proceed with that one. That means this one have possible 9 solution, maybe the other one will be 6 solution. Okay, do some reading, configuration. Finalize your bearing selection after analyze the shaft has been carried out. That means after you do the shaft, I not cover that one in the project. Then you finalize based on this one. Remember this one? Only double check which bearing because you have 6 solution for the radial and thrust. You have 9 solution for radial only. Okay, choose the right bearing. Iterate whether you want to increase the shaft or you want to choose the larger one. It's up to you. That will be the interaction between the shaft. Okay, or the other way that you do the bearing based on suggested whatever here. Check the shaft. It's safe. That is fine. All right, that's all about the bearing. We finish our bearing. All right. For next class, going to be belt. It's going to be catalog-based classes. You have download catalog from the e-learning. Okay, we're going to refer that catalog. And I have uploaded my bolt and welding lecture to the Google Drive, as well as bolt and welding slide on the e-learning. Okay, and the minor project. I won't give you that lecture, but you have to refer my lecture online. Okay, that will be the minor project. All right, that will be the minor project for another 5%. All right, I think that's it. All right, next time will be belt. Make sure you download the the catalog from our e-learning. Right, I stop this one recording. All right, any question before we end the class? Okay, everybody good? All right, seem to be okay. Okay, if okay, I just share before end the class. Okay, I just share this the attendant, the QR for attendant. Okay, thank you very much. Assalamualaikum and goodbye. Stay
Thank
safe.
you. Thank you, Doctor.
Thank you.